So welcome everyone to the second session. The second challenge was multi-view stereo, and it turns out that was the only failure case of our challenge. So most of the four of the other 5 challenges had more than 10 entries, and ours, the multi-view one, was the only one where we had only 3 entries, and 2 of them don't qualify. The winner and the second prize don't qualify for prizes. But we decided to, instead of canceling the session, to have the session anyway and actually talk about the issues. Why did this not take off like the other ones? And maybe the next time around, what can we do different? So the winner was a method that I was a co-author on, although I had a small portion of the contribution. So it's by Andreas Kuhn, who can't be here, so I will actually give a short talk introducing his method. And the runner-up was Colmap, and Johannes will give a short talk about that. And so we will do this slightly different than the other sessions. We will still have the 2 talks. They will probably be a bit shorter. And then hopefully we can have a little bit of a discussion on what the issues were that prevented more people from participating and how we can go forward from here. So let me switch presentations here. So the winner was LTVRE, so local total variation reconstruction, is a method that is really Andreas Kuhn's PhD thesis work. And the first portion of that was, so Andreas was supervised by Helmut Meyer, and he also worked with Heiko Hirschmüller, and the first portion of it was published at GCPR in 2013. And then in 2014, there was an update where we added the learned stereo quality estimation. That's where I became a co-author. And then there is a IJCV paper that describes the whole thing, and if you Google Andreas' thesis, you can also get your hands on that. So I will try my best to explain Andreas' method and how it works. And I guess I meant to say at the beginning, one other interesting feature of the multi-view challenge was that none of the methods use any neural nets or deep learning, so I take that as a badge of honor. Maybe the field hasn't progressed there quite yet to see how we can build a big neural net that can take hundreds of input images and do something useful. So this will be the only time today where you will not hear about neural nets. All right, so the goal of this particular system was to handle very large data sets, hundreds of high resolution images that typically outdoors, and typically from different viewpoints. So some of them might be aerial images and some of them might be taken from the ground. And how can we do 3D reconstruction from those? So here's an example. This is all data from the Universität der Bundeswehr. So here are 4 of 822 input images, 10 megapixel images, some of taken from the from drones and some from the ground. And here is the model that comes out at the other end in reasonable amount of time. So we have 8.2 gigapixels input, about 1 billion triangles in the final mesh that gets constructed, and the whole thing takes about 6 hours on 100 cores. So it's really optimized for parallelizability. And so let's quickly go through how this actually works. So here's an outline of the different processing steps, and actually I'll just show you a picture on each to make this easier to digest. So the input to the system is images and camera poses. So the system does not include a structure for motion component, so we'll use some other technique to get the camera poses, and that's supposed to be the input. And the way it works, it starts from stereo. It picks off all those stereo images and poses. It picks image pairs that have similar enough viewpoint that the stereo algorithm will work. And of course, since he worked with Heiko, he basically used semi-global matching, SGM, out of the box. And that is the input. So then it turns into a big range data fusion problem. And one of the contributions is to actually estimate the quality of the disparity estimates in this fusion problem. Once we have those estimates, this picture is supposed to be a top-down view where you see different, maybe you can see different rays of view. So basically you propagate a Gaussian along these rays of view where you expect the surface to be, and you extract the surface from there. In a big voxel space, and to make it scalable, the voxels will be both tiled, and there's an octree representation. And then finally, there's a little bit of filtering to remove points that occlude each other. And finally, the whole thing gets triangulated. So the output of this method is really a triangle mesh, so that we can later put it in a graphics card, although most graphics cards can't handle 1 billion triangles, so you have to look at it in batches. So as I said, a big motivating factor here was the scalability of the whole thing. And a lot of the early stages are parallelizable, so stereo matching, you can just farm out all your stereo pairs to your different processors. Then we use an octree representation. So this is a 2D view, but of course it's in 3D for the whole viewing volume. And the resolution of the octree is determined by the resolution of the disparity maps at that location in space. And again, the whole octree will probably not fit into memory. So if needed, so this tiling will depend on the amount of memory and the amount of cores you have. So as far as the point estimation goes, you can tile it just fine and process everything separately. Where it gets a little bit tricky is in the meshing at the end, because you might have some triangles. So you have some points here in this overlap region, so you have some triangles that straddle this, so that the overlap is designed so that the triangulation works. All right, so the disparity quality modeling. So in order to do this range map fusion, it's important that we know the accuracy, have an accuracy estimate for each depth value. So we use a standard model for that based on the camera geometry. But in addition to that, we also try to get a handle on how good the disparities are. And so if you run, so this is somewhat tailored to SGM. So if you run SGM, it has a frontal parallel bias. So if this surface is slanted, you might get some staircasing. There is subpixel estimation in there, but usually there's still a ripple. So the approach here is to look at the disparity maps, look at the ripple in the disparity maps, and from that get an estimate how good your quality is. So for example, if you have an input image that has some texture on it, like over here, the stereo will perform very well and it will give you a very smooth surface. But if it's either untextured or highly slanted, then you typically get higher ripples. And so we compute the total variation over neighborhoods as an estimate for how much of a ripple there is. And from that, we then want to predict how uncertain these disparities are. And that particular model, so it's a Gaussian, the mean and the standard deviation of the Gaussian is learned from the Middlebury 2014 stereo data. So that's all I will say about that. So then we have all these disparity maps. You put them in space. They each have their own error model, and they do a standard volumetric fusion. So it's similar to Corliss and Hanrahan. But this one is using a Gaussian model. So you can imagine that there is some sort of a Gaussian where you think the surface is, and in the voxels you actually then accumulate the cumulative distance function, so the integral over that, and that gets averaged over all the pixels that disappear. So this is a very simplified explanation. Where it gets tricky is how do we combine this when we have different levels in the octree, so different resolutions. And so we prefer, of course, the finer resolutions over the coarser ones. And so there is a clever way of merging all of these. So then in the end, we have these cumulative distance functions, and red means we're probably in front of the surface, and blue means we're probably behind the surface, and we're trying to extract the surface where that has the highest probability in the octree. And finally, there's some filtering, so that we might, after we have extracted different surface points for the different views, some of them might conflict, and we pick the one with the highest probability and get rid of the other ones based on probability constraints. So this is different from, say, a global method that takes all your voxels and tries to find a watertight surface. This is really designed to be sparse or local, so you might get very many different surface patches, there might be holes, and so on. Finally, we have this point cloud. It gets turned into a triangle mesh using an incremental meshing method that's also designed to handle multi-scale representations. And so here's some results. So the thing I find impressive about the method is just how the size of the data sets it can handle. So we have here, for example, 112 images, 5 megapixel images of a house. Again, some from a ground, some from the sky. And this is the result we get. And for comparison, if we use PMVS, it looks like that. If we use a method by Fuhrmann and Grüßele, it looks like that. And so ours gives, very more kind of detail, geometric detail. Here's another very large data set. So this is a church on the Uni-Bundeswehr property, and so the green and the blue views, the blue ones were taken from a drone, the green ones from the ground, and then the red ones were taken just around the entrance of the church with a 36 megapixel camera, and again, it's to demonstrate that it can handle these conflicting resolutions. And so this is our method here. Our results, PMBS, Fuhrmann Grüßele, and then here's some details. So I'm not sure if you can see this, but it actually can reconstruct this door handle here on the front of the church, and then PMBS and Fuhrmann Grüßele have more trouble, especially with these untextured surfaces. And here's another comparison to just show the learned uncertainty model. So that's what this is supposed to say. The sigma is derived from the total variation of the disparity map compared to a fixed sigma. So you can see if you have a fixed sigma, in this case, it tries to get a lot of geometric detail, but then you get more holes. And so the varying sigma gives improved results. So in summary, this is an accurate, local, scalable, multi-view stereo method. It starts with pairwise disparity maps. It does probabilistic multi-scale fusion of depth estimates using this learned quality, and it's highly parallelizable. Now, we almost awarded the prize to this, even though I'm a co-author, but I said, I really didn't have very much to do with it. We could just give the prize to Andreas. But the other problem with the method is it doesn't obey the robust vision submission guidelines, whereas the code needs to be available for inspection. We weren't going to give out the code, but we want to make sure that, well, this is really about methods that use training data, that there was no cheating going on in terms of training and test data. So this, we can neither give out the SGM implementation nor the other implementations, so that is another reason. All right, so I'll hand it over to Johannes for the other method. Thank you very much. Oh, is there any question right now? I'm happy to take questions. We can also ask the questions at the end.